Hi everyone, I'm kiren.padayachee and I'd like to show you my Encountered-Type Haptic Feedback system for the Oculus Quest 1. Let's get into it, shall we, before I give you some of the details. Here we see the user starting off with the system already calibrated. This system uses the hand tracking feature of the Oculus Quest, so no virtual reality gloves are needed. The user enters dominant hand, gender and age data before starting the familiarization step for the haptic feedback system. During this step, the user is guided to click on certain buttons in sequence. The virtual button that is below the user's index finger will cause the rig on the table to position a physical button for the user to interact with at the correct position. This enables the user to experience realistic passive haptic feedback. Once the user has become familiar with the system, they are given the opportunity to play a game using a virtual control panel with haptic feedback. The user can position a spaceship by moving or dashing left and right to aim and shoot incoming aliens. The player is then rewarded with weapon upgrades as more aliens are shot down.
3, 2, 1, go! Three, 2, 1, go! Three, 2, 1, go!
So, now for some details. I've been a professional software engineer for the last 15 years, and I've become interested in virtual reality as the consumer VR hardware has become more mature and accessible over the last few years. Specifically, I became interested in the area of haptic feedback for VR. So I decided to do my master's in electrical engineering degree on the topic of encounter-type haptic devices. So what are encounter-type haptic devices, or ETHDs? These are devices that have real-world replicas of virtual objects and can dynamically position the real-world objects when the user interacts with one of the virtual objects in the scene. This way, the user can experience realistic haptic feedback in the virtual world that they are interacting with. So for this project, I made an app in Unity for the Oculus Quest 1 and built a CNC rig to provide the encounter-type haptic feedback. The Oculus Quest was chosen as it has hand tracking built into the device, requiring no gloves or additional hardware. The rig was made from stepper motors and belt-driven linear actuators from some popular online sources. The goal for the rig was to be as cheap as possible while being fast enough so that the delay of the rig was minimal, such that it does not impact the user experience too much. A rig that is super fast with almost zero delay is ideal, but user safety is also something to consider. The rig's motors are controlled by an Arduino Duet with the G2 Core firmware. A custom-made Java application sends G code to the G2 Core firmware to position the correct button underneath the user's finger that corresponds to the virtual button that they wish to interact with. The Unity app and the rig software can run separately from each other until they are linked together to communicate over Wi-Fi with a custom UDP packet protocol. When starting up the system, it first needs to be calibrated. The rig is first started on a homing cycle to find two sensors in the top left corner, which will be set as the origin point. It is then brought forward within the user's reach. Next, the app is started. The Oculus Quest controllers are first placed on the button panel attached to the rig to align the real and virtual world coordinate systems of the rig and the app. The two central positions of the controllers and two of the panel's buttons are all that is needed to align the center position and rotation of the systems. Since this is for a master's research project, the user is first required to enter age, gender, and dominant hand data. The dominant hand data is needed as only one arm is required for this application. The user will then go through a tutorial to become familiar with the haptic feedback system. During this tutorial, a predefined sequence of buttons will be highlighted for the user to click on. The user is then required to move their index finger above the highlighted button, which is currently positioned below the transparent table. This will then result in the rig moving to the correct position. While it is moving, a safety indicator above the table will tell the user to wait. When the rig has stopped moving, the button will pop up above the table and the safety indicator will notify the user that it is now safe to click the button. The user is then able to click the button so that the next button in the sequence is highlighted. These steps are then repeated. Note that this system is designed this way to ensure that the user will be able to safely click the button when it is in place and the rig is stationary. If the user's hand is below the safety indicator, the rig will not move at all to avoid a collision, and the user will be prompted to raise their hand above the safety indicator. Once all buttons in the sequence have been clicked, the user is then given freedom to click any button on the panel in any sequence at speed that they wish. The user is then given the opportunity to play a Space Invaders-like game. On the panel presented to the user are buttons for moving, dashing, and shooting. Shooting 10 aliens will unlock the double shot upgrade button. Shooting a further 10 aliens will unlock 2 more buttons for a larger spherical shot, or a wide laser shot to clear out many aliens at once. The aim is to clear out all aliens and to avoid as much damage as possible. If the user takes too long, the aliens will get too close to the spaceship and the round will end. The user will first go through a practice round to get used to the buttons and game mechanics, as well as to practice using the haptic feedback system in an actual time-critical application. The user can then practice as much as they want until they are comfortable. Note that the physical buttons on the rig do not have any electronics connected and are purely used for realistic haptic feedback. The application only uses the virtual positions for collision detection, which is why accurate calibration on startup is necessary.
Three,
2,
1.
go!
3,
2,
1.
go!
When the user is ready, they can start the actual trial. For this experiment, the maximum reach speed is varied, and the user will rate their experience based on the responsiveness of the system. The questionnaires used for these ratings are the widely used User Experience Questionnaire and the Presence Questionnaire. Many previous studies for Encountered-Type Haptic Feedback systems have used 6 degree of freedom robotic arms. Cheaper consumer robot arms, which are priced at around $100, are slower and have a smaller spatial volume to work with. Larger industrial robot arms are much faster and have a larger spatial volume to work with, but these are very expensive and can reach prices well over $100,000. This rig was built using parts from popular online sources and costs around 15,000 South African rands or $1,000. As you can see, it moves quite quickly and has a working area of 1 square meter. This design results in good performance for the price compared to other solutions. To upgrade it to move in 3D would not require too large of a jump in pricing. This brings me to the end of my presentation. I hope that I've piqued your interest in the topic of haptic feedback for VR and in this Encountered-Type Haptics project. If you are interested in reaching out to me regarding this project, please send an email to kiren.padayachee@gmail.com. Thanks for your time.